Chapter 5 is all about thermochemistry, where we'll be looking at different chemical and physical changes and the energy changes that accompany those, usually in the form of heat. There are many different forms of energy. Some of these types we'll be discussing in this chapter, while others will be talked about in later chapters. The focus of Chapter 5 is mostly on thermal energy, or heat energy. Many chemical reactions release heat as a product. Some of them actually need energy in the form of heat to get going. Next chapter, we'll be discussing electromagnetic energy and the electromagnetic spectrum, where we learn about visible light, infrared radiation, and radio waves, for an example. If you take Chemistry 112, we'll discuss electrical energy more in depth. We already learned about redox reactions where electrons were being transferred. This is an example of how we can have electrical energy. We'll also talk about chemical energy in this chapter. The bonds that are holding together different compounds can be broken, and when they're broken, energy could be given off. Nuclear energy has to do with changes in the nucleus of a compound. You can have something like alpha decay or beta decay, for example. And energy can change forms, we'll see. Mechanical energy is an example of kinetic energy, where the energy is used to move something. All of the different types of energy we saw previously are important to our daily lives. We'll try to figure out how we can figure out the amount of energy contained within food. How could we figure out the amount of energy that is released when gasoline is combusted? We could look at energy of all kinds of different chemical and physical processes and figure out if energy is needed or released and what the result of that is. When we're talking about thermochemistry, we're talking about studying the amount of heat absorbed or the amount of heat released during chemical and physical changes. Heat is just one type of energy. Energy is the capacity to do work or transfer heat. Some of these types of energy you might have heard of before, and some might be new. For example, kinetic energy is the energy associated with motion, whereas potential energy is the energy associated with position. Heat energy has to do with temperature, and something that's going to be new this chapter most likely is called internal energy, which has to do with molecular composition. Since energy is the capacity to supply heat or do work, those are going to be the two components we have to consider for any type of energy we're discussing. The symbol for heat is lowercase q, and the symbol for work is lowercase w. The two major types of energy that you've most likely seen before are potential energy and kinetic energy. Potential energy is stored energy that can be released. It usually has to do with the position an object has, whereas kinetic energy is the energy something has while it's moving. Energy can change forms from one to another, but it can never be created or destroyed. Just like we saw with the law of conservation of matter, where matter can change forms from reactants to products, but it was never created or destroyed. The same thing is true with the law of conservation of energy. The energy of the universe is constant. For example, on the left, we have a ball that's held up high. Because the ball is held up high, it has some potential energy that's waiting to be released due to its position. But if we throw that ball and drop it, that potential energy will get converted into kinetic energy. So on the far left, we see that we have no kinetic energy and we have a high amount of potential energy. And then the two swap. Kinetic energy starts to increase while potential energy goes down until it reaches a minimum and a maximum. And then they swap again, where we have a great amount of potential energy and no kinetic energy once the ball stops moving. Therefore, energy can be changed from potential into kinetic or vice versa, but we're never losing any energy. The law of conservation of energy also holds true for chemical systems. In this example, our equation represents the combustion of octane. Octane is a hydrocarbon that contains only carbon and hydrogen. Combustion means it's being reacted with oxygen, and the products are gaseous carbon dioxide and gaseous water. We can also say that energy is a product of this reaction because the combustion releases a great amount of energy. Octane and oxygen both contain energy within their bonds. This would be described as a potential energy. And when those bonds are broken and the new carbon dioxide and water bonds are formed, a great amount of energy is also released. This energy is a kinetic energy which can be used to power the cylinder's pistons within your car. The gaseous carbon dioxide and the gaseous water cause the pistons to expand and move because of the great amount of volume that's being generated due to the gaseous products. This allows our chemical reaction to supply our auto engine with mechanical energy. Before we can fully discuss the energy of chemical reactions, we need to understand a few key definitions. Thermal energy is the kinetic energy associated with the random motion of atoms and molecules, whereas temperature is a numerical measure of the average kinetic energy of a sample. Temperature tells us quantitatively if something is hot or if something is cold based upon the temperature we read. We're reading a measure of that thermal energy when we take a temperature. So for example, if we have a bucket of hot water and we have a bucket of cold water, the particles of hot water are moving very fast. They have a lot of thermal energy. They're vibrating and they're bouncing off of one another. So if they have a high kinetic energy, the temperature we would measure would be high because those particles are moving a great amount. Whereas if we have a sample of cold water, now those particles are barely moving at all. They're vibrating much less and bouncing around a lot less. We would say they have a low kinetic energy because their motion has slowed down considerably. And when we took the temperature, we would measure a much lower temperature than we would with the hot water. So it's important to differentiate between thermal energy and then temperature, which is a measure of the amount of thermal energy something has. If you increase the temperature of a sample of matter, it will cause the thermal energy to go up as well. This is exactly how a thermometer would work. This is a standard alcohol thermometer, and many substances that are liquids will expand as their thermal energy increases, and they'll contract as their thermal energy decreases. So therefore, as the temperature goes up, the liquid within the column of the thermometer will expand and we'll be able to read the temperature. As the temperature goes down, the liquid within the column will contract and it'll go down and we could read the new temperature. So we talked about thermal energy and we talked about temperature. The last thing we need to differentiate between is heat. We said the symbol for heat is lowercase q. Heat describes the transfer of thermal energy between two bodies that are at different temperatures. Some people will say the word heat flow, but the word heat is already implying the flow or the transfer. Heat is not the same thing as temperature, but we can use temperature in order to get at heat. Heat is directly proportional to the temperature of something. If you see the capital delta, this is a Greek letter and it means the word change. So our heat is proportional to our temperature changes. Whenever heat flows, the thermal energy is always moving from a region of higher temperature with a high kinetic energy to a region of lower temperature which would have low kinetic energy. Heat never flows in the opposite direction. The kinetic energy always starts at some higher object and moves to the object with less. For example, if we imagine that we are going to take our hand and stick it into a bucket of hot water, what would happen? These particle diagrams are trying to show us what we could expect to see on the molecular level. So the hot water has a high kinetic energy because it's warm. Therefore, the tails of our particles are long because they have great kinetic energy. Our hand is colder than the hot water, so in comparison, our hand has low kinetic energy, and therefore the particles are not moving as much, so the tails are smaller. Eventually, the thermal energy will start to flow spontaneously from the hot water to our cold hand. So the energy flows from the region of high kinetic energy to the region of low kinetic energy. This occurs spontaneously and is actually one of the three laws of thermodynamics. Eventually, the temperature of the hot water will go down, and eventually the temperature of our hand, if we leave them in contact, will go up. This is known as thermal equilibrium. Over time, the temperatures will eventually become the same. Matter undergoing chemical or physical changes can either absorb heat or release heat. An exothermic reaction is a reaction in which energy is released, or heat is a product. If our system is our chemical reaction, that would mean that the system would generate heat and the heat would be released from the system to the surroundings. Your flask would feel hot if you feel it in an exothermic reaction. Combustion reactions are an example of exothermic reactions. Heat is a product because it is released. Endothermic reactions are reactions that consume energy, or heat is a reactant. In an endothermic reaction, heat is absorbed by the system from the surroundings. If you were to put your hand around a flask that's an endothermic reaction, it would feel cold. An example is carbon dioxide combining with water in photosynthesis. Heat energy is required to drive this reaction where we produce glucose and oxygen. These images depict something called the potential energy diagram. We can compare the energy of reactants to the energy of products. On the left, we have an exothermic reaction. We know that an exothermic reaction is one that generates heat energy. Notice the starting energy of our reactants is higher than the ending energy of our products. The difference in energy between our reactants and products is exactly how much heat would be released. In an endothermic reaction, the energy of our reactants is lower than the energy of our products. That means that our chemical reaction must absorb some energy to get going. Once again, the difference between the products and the reactants is how much energy must be absorbed. The joule is the SI unit for energy. The joule is abbreviated with the symbol capital J. It is defined as the amount of kinetic energy possessed by a 2 kilogram object moving at a speed of 1 meter per second. If we use the formula for kinetic energy, which is equal to 1/2 times the mass times the velocity squared, and we were to plug in our mass and velocity, we would have 1/2 times 2 kilograms times our velocity, which is 1 meter per second, squared. That'll give us our derived SI units for energy. Our 2 will cancel with the 2 in the denominator from our fraction, and our units would be 1 kilogram times meter squared over second squared. Instead of writing that out every time, those are the base units which make up the joule. That is our derived SI unit that's used for heat, work, really any form of energy. Another unit of energy you're most likely familiar with is the calorie. If you've looked at the back of any food label, you've seen that energy is listed in the form of calories. There's 2 different types of calories that are discussed. One where there is a capital C, such as on the back of your food label, and then one that's written with a lowercase c. One lowercase c calorie is equal to 4.184 joules exactly, from definition. But the nutritional or dietary calorie that's listed with a capital C is equal to 1,000 calories with a lowercase c. So one nutritional or dietary calorie is equal to 1 kcal, which would be equal to 4,184 joules, or 4.184 kilojoules for short. You may have problems that ask you to convert between units of energy, either using calories that are dietary, calories with a lowercase c, or joules. You don't have to memorize any of these unit conversions. You would be given them on a quiz or exam. We defined heat and we defined temperature. We know that we cannot measure heat directly. We can only get at our heat changes by looking at temperature changes, or delta T's. 2 concepts to help us explain this are heat capacity and specific heat. Heat capacity uses the symbol capital C. The heat capacity of a body of matter or an object is the quantity of heat it absorbs or releases when it experiences a temperature change, delta T, of 1 degree Celsius. Heat capacity then is object specific. It depends upon the amount of matter present. Therefore, we would say it is an extensive property because it depends upon the mass. The heat capacity then could be written as the heat change, or Q, divided by the temperature change, delta T, where delta T equals T final minus T initial. If we rearrange our heat capacity formula, we could solve for the heat. Heat, or Q, would be measured in units of joules. The heat capacity, capital C, has units of joules per degree Celsius, and our temperature change is usually in degrees Celsius, but it could also be in Kelvin. We take some final temperature minus some initial temperature to find the change. Heat capacity is a little bit less useful than specific heat because it is an extensive property and it does depend upon the object or the mass for how much heat energy will change when the object is changed in temperature. This is why we will usually use specific heat. Specific heat capacity, or specific heat for short, uses the symbol lowercase c. The specific heat of a substance is the quantity of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius. Notice this time it says nothing about an object. We know that we're raising the temperature of 1 gram exactly of whatever that substance might be. Therefore, this is an intensive property. It does not depend upon the amount of matter present because the definition specifies that we always have to have 1 gram. It only depends upon what the actual identity of the substance is for how the specific heat will change. Therefore, the formula for specific heat, lowercase c, is equal to the heat, or Q, divided by the mass times the temperature change, where our temperature change is still some final temperature minus an initial temperature. If we rearrange this and solve for the heat, we can use our formula Q equals mc delta T. Q is the heat in units of joules, m is the mass in grams, C is lowercase, therefore it's the specific heat. Units of specific heat are joules per gram degrees Celsius, based upon the definition, and T is our temperature change, T final minus T initial, either in units of Kelvin or degrees Celsius. The specific heats of many substances are known and tabulated. Specific heat is measured in units of joules per gram degrees Celsius. And if we were to compare the specific heats of a few things, look at the specific heat of lead. It's 0.128. The specific heat of gold, 0.129. The specific heat of copper, 0.387. All three of these are examples of metals. Metals tend to have low specific heats. That means that it doesn't require a lot of energy to heat them up. Also, they'll lose their heat very fast and cool down fast. If you imagine a metal bench in a park on a hot summer day and you were to sit on it, it's most likely going to be hot. That's because it doesn't require a lot of energy in order to warm that metal up. But it'll also fall in temperature very fast once the sun goes away. The specific heats of many of our nonmetals are much higher. For example, carbon has a specific heat of 0.711. Our specific heat of olive oil is 2.0. And lastly, our specific heat of water is 4.184. Specific heat of water is very, very high, and this is due to the intermolecular forces within water. If you've ever boiled a pot of water on the stove, you know how long it takes for the water to begin to boil. It requires a lot of energy input in order to raise the temperature by just 1 degree Celsius. But that also means that water holds its heat much longer. So once a pool warms up in the summer, it usually stays warm for the whole time because the water doesn't lose energy very fast either. You have a handout in your notes on Blackboard that's titled Specific Heat of Various Substances. You will be given this handout on quizzes or exams. It's best to keep it next to you while practicing in case the specific heat of any substance needs to be looked up for a problem. Now we are going to try a few examples involving specific heat. If a piece of copper wire with a mass of 20.9 grams changes in temperature from 25 to 28 degrees Celsius, how much heat has it absorbed? The specific heat of copper is 0.387 joules per gram degree Celsius. Since we're doing a problem involving our specific heat, Q equals mc delta T is going to be the equation we want to use. And we mostly have to check and make sure that our units are okay. Since specific heat is measured in units of joules per gram degrees Celsius, that means that our mass is going to have to be in units of grams, and our temperature change usually will be in units of degrees Celsius. In this case, our energy that we calculate is going to be in units of joules. So plugging into our formula, we know our mass of our copper is 20.9 grams. Our specific heat of copper, which was given to us, is 0.387 joules per gram times degrees Celsius. And our temperature change, which is going to be T final minus T initial, will be 28 minus 25 degrees Celsius. Or we could say our delta T is 3 degrees Celsius because that's the difference between the final and the initial. When we calculate Q then, notice how our units will cancel. Our grams cancel with our specific heat, our degrees Celsius cancel with our specific heat. All we're left with is a unit of energy, which is what we want for heat. The amount of heat energy released when the copper wire changes its temperature is 24.2 joules. A couple other keywords to understand is whether the energy is absorbed or released. In this example, the energy was absorbed, and we knew that because our copper wire increased in temperature. Therefore, the sign on our heat that we calculated was a positive value. This positive value means that heat is absorbed. We'll see later that the signs on Q can be positive or negative, but they don't mean positive and negative in the sense of what we learned in math. They really just tell us the direction of heat flow and whether heat is being absorbed or being released by a process. If a 25.2 gram piece of silver absorbs 365 joules of heat, what will the final temperature of the silver be if the initial temperature is 22.2 degrees Celsius? The specific heat of silver is 0.235 joules per gram degrees Celsius. So we're going to want to start with our formula for specific heat. Q equals mc delta T. But since we're finding a final temperature, let's write this as Q equals mc T final minus T initial. We can rearrange to determine T final. Q divided by M times C will be equal to T final minus T initial. And then if we add T initial to both sides of our equation, we would get T final equals Q divided by MC plus T sub I. Next, we want to make sure all of our units are okay. Everything needs to cancel with the units on specific heat, which are joules per gram degrees Celsius. So our heat, or Q, is 365 joules. Our temperature is 22.2 degrees Celsius, and our mass is 25.2 grams. So everything is in the appropriate units. T final will equal our mass, or our heat on the top, 365 joules, divided by our mass, 25.2 grams, times our specific heat for silver, 0.235 joules per gram degrees Celsius, plus our initial temperature, which was 22.2 degrees C. This gives us our final temperature, or T sub F, as 83.8 degrees Celsius. We also knew that it had to be a higher temperature than what we started with because the silver absorbed heat. So therefore, our sign on our Q was once again positive. A piece of unknown metal weighs 348 grams. When the metal piece absorbs 6.64 kilojoules of heat, its temperature increases from 22.4 degrees Celsius to 43.6 degrees Celsius. Determine the specific heat and the identity of this metal. If ever you are asked to figure out an unknown identity, the thing you're going to want to solve for is the specific heat, because you have a chart of specific heats of various substances that you can then go match up and figure out what specific heat matches to what identity of the metal. So starting with our formula, Q equals mc delta T, this time we're rearranging and solving for C, which is our specific heat. That will equal Q divided by the mass times the change in the temperature. So our specific heat in this example will be equal to, we have 664 kilojoules of heat, and we want to make sure that we put our units of heat energy in terms of joules so they cancel out. So we have 6.64 times 10 to the third joules. Our mass is already listed in grams, 348 grams. And our temperature change, T final, 43.6 minus 22.4 degrees Celsius. That should give us a specific heat of 0.90 joules per gram degrees Celsius. And looking at our chart of specific heats that's on Blackboard, the metal that specific heat is closest to is aluminum.